share my screen briefly. Okay, welcome to METASIS Webinar number 6. Today we have a speaker, Professor Suddhasatwa Basu from Department of Chemical Engineering, Indian Institute of Technology. So he will be talking about the hybrid metal phosphonates and perovskite-cobaltite material as electrode materials for energy conversion. As you would know, Professor Basu is a chair on clean energy at IIT Delhi and a former director of CSIR lab IMMT in Bhubaneswar, and also CSIR CIMFR in Dhanbad. As we all know, is expert in hydrogen and fuel cell, lithium and sodium-ion batteries, including electrosynthesis and waste-to-wealth technologies. He has published so many journal articles and have patents. His H index is over 57. He holds multiple patents. He is a fellow of Indian National Science Academy, National Academy of Science of India, and many other organizations. He has been awarded with Fulbright Academic and Professional Excellence Fellow and many other awards. So as part of housekeeping today, you can, I believe you're able to access this. So all attendees are on mute. Please use the chat function for question and answer session, which will be happening toward the end of the session. If you've got any technical issue, please log in or join in again. We will share the recording of the link via YouTube. And also, we aim to finish within the 1 hour slot we have today. So without further delay, I would like to invite Professor Basu to share his screen and get us started with the presentation. Thank you.
Thank you, Professor Faisal, for inviting me. Let me share the screen. Did you allow me to share my screen?
1 second. Yes, I think you should be able to share now.
Okay, I'll just check. Yeah. Okay.
Thank you.
Is it visible?
Yeah, it is coming up. Yeah, you can get started now. Thank you.
Okay. So are you able to see my pointer?
Yes, I do.
Okay. So thank you, Professor Faisal. It's a really nice platform that you have created. I just checked. Invited me. Topic very specific to certain structures, perovskites, cobaltite, and phosphonates that we are working towards the storage. Storage in terms of mostly hydrogen, that you store electricity in the form of hydrogen, and then of course utilize the hydrogen. So before going into much details, my first few slides would be on, in generic, how what is that closed system of hydrogen that we are envisaging, and everybody is working on it. And this has been planned for last 40 years, ever since everybody's trying to promote the hydrogen energy. But more so now, at least the hydrogen use part of the hydrogen in industry, that you get, you can produce a lot of renewable energy, whether solar photovoltaic, wind, or solar thermal, and you can, excuse me, you can, of course, give a grid power, but the excess power or the intermittent power of this kind of source, you need to store them, and you might be having also excess power, so you can store them in the form of hydrogen by splitting water. And when you produce hydrogen and oxygen, use that hydrogen for all kind of petroleum chemistry that we do. If you are promoting such kind of source of energy for utilizing electricity for stationary use, mobility for electric vehicle, and many others. And that is what I'm showing you here. And each time you produce, when you have hydrogen as a fuel, it is combustion. It is the oxygen is used to make water, and all the blue lines is about water. That means where you are directly combusting it in IC engine, in fuel cell, and so on and so forth. You go on producing water, and that same water goes and comes back to your electrolyzer. So water balance is perfect, except for the solar energy, that photon that you have used to make energy. Except that, nothing is, you are collecting or you are mining from the surface like we do it for fossil fuel. And we produce a lot of CO2, and that CO2, is kind of or greenhouse gases many times, like CO2, methane, and which then creates a environment around the Earth's surface such that the heat not able to leave the surface, so the surface temperature is increasing year by year and centuries, and one might see that there is so much increase in surface temperature that ice cap melts, and already melting. We know that a lot of glaciers, old glaciers and ice is every year is melting, and our sea line is increasing because water is increasing, and some of the cities, most of the cities are around the sea line or the sea coast, and they would be under then water. So it's kind of a devastating phenomena that could take place. And if we, instead of using fossil fuel, if you take this closed loop hydrogen energy loop, then of course you are a win-win situation. So what we can do, which is also shown you here, the same loop that I've been shown just now, I've talked about. And today, the hydrogen in millions of tons of hydrogen is produced for different purposes, like in refinery, in ammonia. But the source of hydrogen is not a green hydrogen. The source of hydrogen is mostly maybe of late little bit of blue hydrogen, but mostly it is gray and brown hydrogen. That is coming from coal, or it is coming from methane, the natural gas. And that is how they are not good. They are emitting CO and CO2. That is what, when you produce ammonia. So can we use that hydrogen from sources like electrolysis of water with the excess amount of energy that is produced from renewable energy, which is maybe hydroelectric, which may be wind power, and which may be also solar photovoltaic. So we can produce green ammonia if the hydrogen source is green. Green refining, you require hydrotreatment, hydrocracking. Green steel, I generally for steel making, you need to have a reductant, and coal and coke works as a reductant in the blast furnace. So instead of using coal and coke, can we use DRI, direct reduction of iron to iron oxide to iron? And that can be done through hydrogen. And then you can produce green steel, and then green methanol, and many others. Today, the demand of hydrogen, or the hydrogen consumption in 2024 or 2025 is close to about 95 million tons per year, and it is projected by 2030 or maybe 2032. This can go up enormously, and of course we do require to produce green hydrogen and use them in different purposes that just I have mentioned. And in the process, you're not going to make you're going to stop the GHG or greenhouse gas emission. And all the government had taken a vow that by 2050, India 2070 want to have a carbon neutral society. That means net emission, net zero. The net carbon dioxide emission is zero. That means whatever you emit you take it back, okay? And for that, because our requirement of energy is huge, so every year we are actually increasing the CO2 emission. So part of the energy requirement now on can come from the renewable sources, and part of the CO2 that we are emitting, if we have to stop that because of the industrial process, can use hydrogen instead. So towards that, our group has been developing many material by which we would be able to produce hydrogen at lower cost, because if that we have to do it today, hydrogen cost is very high. It's about $5 to $7 per kg. Idea is to bring down the cost to about $2 per kg, so that, or $1.5 per kg, so we match the price of natural gas at least. And this it is an open market. So if there's an open market and there is a competition, you of course need to come to close to the whatever is available at cheaper source, and that is how we need to bring down the cost of hydrogen making, because hydrogen is not a primary fuel. Like in the case of natural gas, in the case of gasoline or crude petroleum, they are naturally available in the Earth's surface or in Earth crust, but not hydrogen so far, although people are claiming there are here and there are hydrogen deposition, but it is so far not being validated that or being mined, only predicted. So our aim of the research should be how we can bring down the cost of hydrogen generation by splitting of water, by electrolyzer or any other technique, which will be, because it's not a primary fuel, which will be similar to the current economy that we have based on the fossil fuel. So towards that end, in our group, we work a lot of different kind of structure. We work on spinel, nickel manganese oxide. We work on layered oxide structure like NVPF, which is sodium vanadium phosphate or fluorophosphate, NVP and NVPF. This material is layered structured or polyanion structure, rather. Polyanion structure is being used for sodium-ion battery cathode material for storage of energy. Nickel manganese oxide is spinel structure, is an open structure, can be used again as cathode material for storing zinc for the zinc ion battery use. I'm not going to discuss much today on that, but zinc ion battery I'm going to discuss. And then we have showed you an NSCF, a sort of cobaltite ferrite or neodymium-cobaltite, which is doped with iron and doped with strontium. So neodymium site is doped with strontium, A site, and B site is doped with iron. And so we got iron and strontium doped neodymium-cobaltite. It's a structure that we have used in the solid oxide cell and solid oxide fuel cell. So we usually use cooking, baking, and temper technique to create different structures. So if you do cook, like you do hydrothermal, solvothermal, sol gel, you do baking, like it's sintering, calcination, combustion, synthesis, is kind of a baking technique to make material. And then on that material, you make a fine structure, right? You make a film, thin film around it, core shell structure, many other things that you can make a composite structure or a doping that you can do it with evaporation technique, DC sputtering or magnetron sputtering technique. You can do spray pyrolysis, you can do atomic layer deposition, pulse laser deposition, PLD, LD and all, and you can do a tadka. We call it tadka or sputtering or tempering that you can do, and that's what we do mostly in our lab, right? So let us start with the first structure, with the phosphonates. So I'm showing you some phosphonates here, and in our lab we can actually take a multidentate ligand, and based on the ligand structure, we can make a phosphonate morphs like metal organic framework. We can take amine structures. We can take micelles, surfactant aggregates. These are all kind of templating technique. And these are all no template, a self-assembly template free structure that it assembles on its own. And based on the structure that we have taken, which is a metal phosphonate, which is shown you here, we make metal phosphonate structure, in this case, the one that I'm presenting, to be used for hydrogen evolution reaction and oxygen evolution reaction, which does better than the state-of-the-art material like iridium oxide, which is standard catalyst for water splitting in PEM electrolyzer or PEM electrolysis cell or PEM water electrolysis cell. Okay, so that's what we will show you, and that's what we have done. So I'm going to talk about little brief. We want to talk about in today's lecture about about today's lecture a lot of technologies, but not very elaborately. But if you want to know elaborately, you have to go back to this paper to know it elaborately. But I will touch upon the crux of the material or the functionalization that we have done and the result that we have got. So in this case, we have started with imidodimethyl phosphonic acid. It is a template. So I was showing you that this is the template, and similar template is one which is shown you here, a template that is mentioned, and with that we add nickel nitride, or we add cobalt nitride, or we use nickel cobalt nitride, and we do a hydrothermal synthesis that you could put them in a reactor or a bomb in autoclave, and then we heat to certain temperature and pressure and maintain pH for certain hours, and we get a nickel phosphonate, cobalt phosphonate, nickel cobalt phosphonate. We also add iron to that. That means if I take iron hydroxynitrate or iron oxyhydroxide or hydroxynitrate along with ethanol as a solvent, and we reflux it for certain hours, like 6 hours, 12 hours, 24 hours, and 40 hours, we can dope along with the cobalt and nickel also iron. But iron doping we have done with a different amount of iron hydroxynitrate that we taken in ethanol, mixing with ethanol, and then with cobalt phosphonate or nickel phosphonate, and then we reflux it at different hours. And the results of the ACM structure at different hours of refluxing, which is A and P 6 hours, okay, C and D is about 12 hours, E and F is about 24 hours, and G and H is about 48 hours. So you can see sort of core shell structure, and that has been broken. So it's kind of a half core shell structure. It's not a complete sphere. It's kind of half sphere. You can see nicely here in this that you get a half sphere. So this half sphere kind of structure that you get, and then we have done EDAX to show that you have all the material that we started with and we wanted to have, that we want to have a iron, cobalt, or phosphonate, because not all of them we made, but the one we got the best results is on iron, cobalt, phosphonate, and the best one we got about 24 and 12 hours of refluxing, and that is being captured here in oxygen evolution reaction as we are showing you here. If you think that oxygen evolution reaction, the best catalyst or the bench scale catalyst is iridium oxide. That has been put in all the PEM electrolyzer. We use iridium oxide. Okay, ruthenium oxide is the best, but it is not stable. And so we use iridium oxide. Some people use iridium ruthenium oxide, but mostly the bench scale catalyst is iridium oxide. And you compare our results with a carbon paper, cobalt phosphonate, iron cobalt phosphonate, different reflux time. And you can see that 12 hours of reflux time, the red color, had the lowest onset. Okay, so lowest onset potential. If you plot the Tafel slope, if you see here, you can see that red line is 43 millivolt per decade, the lowest slope of the Tafel slope that you got, that kinetics is very good for this material, and the activation over potential, the eta is about 249 millivolt, right? Iridium oxide is 351 millivolt, much better, like close to about 75, or about, you can say not even 75, 100 millivolt better in terms of the activation over potential, okay, between iridium oxide bend scale and the iron cobalt phosphonate with 12 hours of reflux. Okay, same thing when you see the Nyquist plot, you can see the polarization resistance lowest for the red color and highest for the only cobalt phosphonate, which is the brown, and which what we are showing you here. Then next three plots are about the stability in chronoamperometry. Here it is mass activity and TOF, turnover frequency, specific activity. All cases you can see that 12 hours reflux with iron cobalt phosphonate gave the best results in terms of mass activity, in terms of the specific activity, and in terms of the turnover frequency. Same catalyst, that's the good part of it. Same catalyst when we do for hydrogen evolution reaction, that means overall and the overall water splitting. Same catalyst, I cannot beat platinum. Platinum is the best, which is this brown color. On the right after platinum is iron cobalt phosphonate, 12 hours reflux with the activation over potential 117 millivolt. Of course, I cannot beat platinum best, which is the 47 millivolt, but after platinum best is our iron cobalt phosphonate. Saying that I cannot beat platinum, but after platinum we have the lowest slope in a Tafel slope, which is the 41 millivolt per decade. Again, about the polarization resistance in EIS, electrochemical impedance spectroscopy, and many others that we have planted here, that iron plays a very crucial role that we have shown you here when we work with EDTA. And so in a nutshell, what we are showing, that we were able to make a catalyst which not only works for oxygen evolution reaction, which also works for hydrogen evolution reaction as well. It's the same catalyst. Now, this was the catalyst development. Now we talk about a niche product that we made as a membraneless microfluidic electrolyzers. I'm not giving the introduction to it, but in the process you will come to know about it. We made a tremendous improvement in this design. The first proposed in EPFL Lucerne, just about 3-4 years before we started. We have reported this in about 2017 or 2016, but we made a step improvement in the design and its longevity. So what it is that we are using a microfluidic channel, and we are using that channel is having a platinum anode in one channel, or two arm as a Y-shaped arm together. One cathode is platinum and anode is platinum, and we use alkaline anolyte and acid catholyte, and actually this is an asymmetric electrolyte. So what the EPFL did is using either alkaline or acid electrolyte, but we showed that when we use acid catholyte acidic and anolyte alkaline, because of the liquid junction potential in favorable position, because we have a difference in pH between the acid and alkali, which gives rise to a liquid junction potential, and we can use this liquid junction potential favorably between this interface, and the movement so that we can have a lesser open circuit potential requirement, because of the presence of the liquid junction potential, the easy movement of ion is possible, because ultimately H plus have to move and OH minus have to move in either direction, so that you can have the complementary reaction, which is the oxidation and reduction reaction for the oxygen evolution, and a hydrogen evolution reaction takes place in respective cathode and anode. And here we are showing that if you can accomplish that hydrogen evolution reaction and oxygen evolution reaction at respective cathode and anode, they will travel through the stream and they will remain separated. No mixing will take place, because they are moving with the stream along the streamline, and without having any physical separation or membrane, just because of the interface of the two fluid, which will be maintained because of the laminar flow, and there will be no intermixing, and you will get the hydrogen coming out, which is the red color, and oxygen coming out with the blue color along with the stream, and the respective hydrogen evolution reaction will take place at the cathode, and oxygen evolution reaction will take place at the anode, as shown you here. Okay, so that was our patent, and that was our publication, that we use asymmetric electrolyte, and the requirement of voltage we brought down to about 0.8 volt. In this case, the requirement is 1.23 volt, otherwise, which is a standard potential for water splitting either in acid or alkaline medium. But because of the use of the liquid junction potential, we could improve this by huge amount, the efficiency. And this design that we have propagated or proposed is what best among the other design that just now I presented or people have come across. We have not changed much design here. We just use asymmetric electrolyte, but here we have changed the design and made it much more robust and more did not allow the intermixing and oxygen and hydrogen to take place. What is this design? That we have a middle channel which is blocked, and we have porous electrode which is shown you here. These porous electrodes are doped with or spotted with the active material, could be platinum, could be phosphonates, and liquid are forced, or the water is forced through this middle channel, but it is blocked, nowhere to go. They can go in the right hand side and left hand side through this porous structure. This electrode is kept in this here, as shown you here, dark yellow line both sides, and water cannot go anywhere else. They have to move through these pores, and you have the active material on the pores, and because of which the oxygen and hydrogen evolution reaction will take place, because you are applying potential for the water splitting. And you have then, while doing so, they are moving towards outward and going through the channel as shown you here, and in a way you are able to separate them, oxygen and hydrogen, no mixing, and we have shown that you get a better current and better voltage. I mean, given voltage, you get a higher current. And we are showing you this nice microfluidic, membraneless microfluidic electrolyzer, and there are about 5 of them together in a stack, and each individual slots for travel or for the transport of ions and transport of water is given here, with the electrode placed parallel to each other as shown you here. So that's a design that we have done, and here we present the results. First we want to show you the video, and we did a simulation, and here it is the experimental video to match the CFD, the computational fluid dynamics simulation of this work, so that what could be the angle, how far away will be each other anode cathode, and then what will the angle and what will the flow rate, so that there is no mixing takes place. So let me see whether I can show you the video. Yes, I'm able to show you the video. you can see that if I have very low flow rate, the bubbles are growing and not detaching because shear rate is not very high. And in a process, there is a mixing taking place between the anodic and cathodic side, or anodic channel and cathodic channel. If I increase the flow rate to 1 to 1.2 to 1.4, these droplets, of course, the hydrogen bubble and oxygen bubbles are forming, but the flow rate is high and they don't intermix. Because of the high flow rate, the shear rate is high, and the small droplet that is forming is detaching and going along with the streams, and no possibility of intermixing. So this we have proven because the bubbles becomes like this, okay, and at the time of detachment, the drag force acting on the outer fluid is exactly equal to the attachment force that is there because of the interfacial tension, and it has overcome and it is detaches. And so bigger the size at lower volumetric flow rate or lower velocity will detach, but the velocity is large, the drag is large, and small droplet will detach, and as a result there is no intermixing takes place when you have a high velocity. Whereas at the low velocity at 0.8 ml per minute, you can see that it is growing bigger and bigger, shear rate is not very high, and then intermixing possibilities taking place. So that is what I want to show you here, that the results, this was the side view, that was the front view that I was showing. So you can see at 2.5 volt, I can get about 750 milliampere per centimeter square, which is a good amount of current that you get such a small cell. And the previous design, which the Hashmi et al. Has shown from EPFL, they got about 70-80 milliampere per centimeter square, and it has improved by 10 times because of our design and because of the catalyst that we're using. So we have tested the purity of the product, because whether there is intermixing taking place, no intermixing taking place. You can see hydrogen at anode, almost negligible peak, and hydrogen at cathode, because cathode is supposed to produce hydrogen and anode is supposed to produce oxygen. But we are testing hydrogen both at the cathode and anode. We have got a very big peak, a lot of hydrogen produced, and almost no peak of hydrogen at anode, so which shows there is no intermixing. And this is kind of a side view. You can see small hydrogen bubble here and there at different velocities, right? And then we did the accelerated testing, and accelerated testing we have done, that is, we have gone through a voltage fluctuation. And if you do the voltage fluctuation, you can see it goes back to the original voltage, and we through the accelerated test protocol that is available at DOE site. So you can go from about 400 hours, there is no deterioration of the cell at all, no voltage change, and the constant current, and almost no corrosion or erosion taking place. We have taken out the electrode, we have done X-ray, no additional peak before testing and after testing both cathode and anode, and we have done XPS as well before and after testing. No change in the formulation or any deposition taking place at the cathode and anode. So this shows that our technology for membraneless microfluidic electrolyzer working very fine, but it has got niche application. It's mostly portable devices, small scale hydrogen generation, where we don't require large quantity of hydrogen. So that was mostly for the sensors and small generation type micro generators. We can use it for those purposes. Okay, so next topic that I want to talk about is about zinc aqueous battery, and we have developed a MOF structure which is like a ACI for the anode electrode or the negative electrode, and which protects from the growth of dendrite. We all know that in the zinc battery, we use the zinc as the anode electrode, and we have zinc hydroxide or zinc oxide formation is there because zinc sulfate is used as the electrolyte and zinc as the anode material. The zinc deposition takes place like a dendrite, and then it perforates through the separator and reaches towards the cathode, and it's shorting it, which is showing you that it could have very strong Young modulus. This zinc dendrite close to about 100 gigapascal of Young modulus. So even if you have a separator which is made of a polymer or a polypropylene, it pierces through it and reaches towards the cathode and touches the cathode and making the cell to die, or shorting of the anode and cathode takes place through the zinc dendrite formation. So that is where you want to prohibit, and that is how the zinc aqueous battery life is very low. And other things are zinc hydroxide, zinc oxide formation, some oxygen hydrogen evolution reaction, and all these things takes place is also required to be stopped, and you have HER reaction as you are showing you here. So our idea is to, this is published in JMCA, our idea is to have a artificial ACI on the negative electrode which protects, like we have similar things in LIB, also in SIB, sodium ion battery and lithium ion battery. Also we have the same idea for zinc dendrite or zinc and aqueous battery, where we utilize the artificial layer which work as a solid electrolyte interface, the ACI. If those who are exposed to this term, they know that how is so much importance is given to ACI formation in a secondary rechargeable battery. So what we do, we have decided to have a zeolitic imidazole framework, or ZIF8 framework on a zinc electrode, which is being used as a anode electrode in zinc aqueous battery. And we feel that this will prohibit the growth of dendrite that we have shown you here. Okay, and which reaches to cathode and shorting is what is happening in the case of zinc aqueous battery, and we feel that that would do that. So what we do, we take a copper foil and then we etch it with a HCl as shown you here. We clean it with HCl, I would say, wash it with HCl, then we etch it with ammonia solution, and then we take a boron buffer. A buffer formulation is shown you here, and you get a zinc deposition. So you have a copper, porous copper, on which you have a zinc deposition. And finally, I take the methyl imidazole with a zinc acetate, and we put it here. And if we do the electrochemical deposition, we get ZIF8 structure or zeolite imidazole framework structure onto the surface, which doesn't allow as much the bare surface for dendrite to grow. I'll show you schematically how this is possible. Let me show that. If I do not have that ZIF8 structure, then the growth of dendrite takes place, sharp peaks, and they're very strong. As I said, the 100 gigapascal is the Young modulus of these zinc dendrites. And if I have a copper foil with a ZIF8 layer on it, and then the growth is not so apparent as shown you here, and there is nowhere to go, so they don't really increase in the peak size that we have shown you here, but they go a little bit of lateral direction in the left hand side and right hand side for the growth. So that is what is captured. Based on this hypothesis, the polarization plot, Tafel polarization, cyclic voltammetry, the onset potential, and the CV, the number of cycles. So that is what is happened. You can see the potential is the lowest for ZIF8 zinc copper surface, which is a kind of ZIF8 zinc copper, which is kind of red, which is having the lowest potential, and um, uh, and of course lowest lowest current and highest potential, I would say, because it's negative potential. So highest potential and lowest current, and we would have almost no corrosion when you have such kind of structure formation that we are showing, or no dendrite formation. And then we are showing that onset potential is pretty low compared to when you have only copper zinc and we have a pristine zinc. One is kind of ash color, one is blue color copper zinc, and compared to that zinc, we have a higher current where we have ZIF8, we have a lower onset potential, we have a ZIF8, this red one, notice. And when we have many cycles, it shows that it goes through many cycles and there's no deterioration for ZIF8, zinc copper anode or negative electrode, so it works excellent. So we have E core highest minus 424.16, because it's a minus, that's how 424 is the highest, and the current is lowest, as I showed you before, and so that is how the corrosion is lowest for ZIF8 zinc copper electrode. Okay, so this is what we have done, and then we run the cell. First is a symmetric cell. You can see the red one is ZIF8 zinc copper, and it's still running till about 1,000 hours. And one can see that blue one, the zinc copper cell, no MOF, it runs up to about 853 cycle and then it ceases to operate. Same thing with no MOF or no ZIF8, the only zinc, and this fails after 169 cycles. Here we are showing for the ZIF8 and between zinc and zinc copper, ZIF8 and zinc copper and zinc, that how we have a polarization resistance and lower onset potential for when you have ZIF8 structure, as shown you here, the over potential, and we are showing you the cell performance at different C rate, and we are showing that even if you have a different C rate that we operate, it is very smooth, that we are increasing C rate and decreasing C rate, and there is perfect stable zinc aqueous battery, which is made from the ZIF8 or zinc MOF structure, which is kind of an artificial ACI, which is protecting the electrode from arbitrary growth of zinc dendrite. Okay, you can see 0.5, 1, 2, these are the C rate, and it goes back to 0.5, and it goes back to the original voltage that we had, okay, given current density. So that's what we developed, and then we did a post-mortem analysis of the cycle material. As I showed you that there was a thin film of ZIF8 which prohibits the growth of dendrite in the vertical direction but allows it to grow in the horizontal direction, and that's how you see FeACM of cycled anode as you move from zinc to zinc copper to ZIF8 zinc copper. And when you go to ZIF8 zinc copper, you have this slanted, and the growth is diverted toward the slanted side, not towards the upward which will then pierce through the polypropylene separator and goes to the cathode. That is what you don't want. Okay, so this is the mechanism we are showing you, and that's about zinc battery. And we developed a cathode material for the zinc battery, and which is working very fine. I'll talk about a little bit now on, I have still some time. So I'll talk about a little bit of work that we have done on sodium-ion battery. I was telling you that we work on NVP and NVPF. This material is for NVPF, which is having vanadium and NVP doesn't have a fluorine, and because of this structure, NVPF, which is polyanion structure, it gives a lot of stability because of the presence of fluorine. But it is also seen that if we use this NVPF with our NaPF6, which is our standard electrolyte with a glyme, and this glyme is like organic, the part of it is reacts with the NVPF cathode material, and then it forms NaF, and then some PF6 minus, and we have an organic material formation. So these are the structure that forms not a ACI, the ACI that you want. You never want an organic ACI. So you have the kind of a solvent in your electrolyte, which is or diglyme, which we are using as a solvent, or in the case of LIB, we use ECPC or DEC. All of them then react and form a kind of complicated structure here, and that is what decrease the durability or span of the sodium-ion battery when you use NVPF. Okay, fluorine is a very reactive, as you know, and diglyme also reacts, and then these kind of things form, which you do not want. Okay, so what we thought that if we can make a thin layered structure of BDC around the cathode material, then it can protect it from formation of the organic phase or organic phase of kind of ACI, which we don't want. We want inorganic phase of ACI to form, like NAF or LIF to form, right? So let us see whether our hypothesis is correct. So we took NVPF, which we are showing you here. We have then coated with BDC. So S1 is pure NVPF, sodium vanadium phosphate and fluorophosphate, and S2 is 10% BDC coated sodium vanadium fluorophosphate, and S3 is 28% boron doped carbon coated sodium vanadium fluorophosphate. So we make this, so this is a kind of hollow structure which is coated as shown you here, and X-ray is done to find out that we have perfectly got the NVPF structure that we wanted, S1, S2, S3, and the coating that we wanted, that we got it perfectly in this case. So now let us do, after studying the cell, we do a reactivity durability of BDC coating with TOF SIMS, time of flight secondary ion mass spectroscope. We use that, no contamination of air, so airless transfer with 1 molar NaPF6 of diglyme. So we utilize that, okay, and we can see here that positive ion spectra. You can see for S1 where there is no BDC, for S1 at 0.2 C for 200 cycles. So there is no peak. There is no peak except for the peak for the carbon that you have got it here. Here we have got pristine electrode which is a positive electrode, where we have S2. S2 means we have a coating of BDC, and you can see that quite well that we could have the positive ion spectra for boron be present, which actually helps us to evaluate or helps us to protect the cathode material from the attack of NaPF6 and the digline that you have. Now we are showing you the negative ion spectra. We were showing you positive ion spectra. You can see a lot of increase. This is 200 cycles. This is a 200 cycles, and all these are all 200 cycles, and between S1 and S2. And you can see that the organic structure after 200 cycles has been increased enormously for S1, and for S2 there is not much increase, slight increase but not much increase. So it shows that when we had a BDC coating, organics ACI is not forming or less forming compared to S1 in S2, where there is a BDC coating. S1 did not have BDC coating, so it is forming lot of, the organic ACI, which get degraded over time. That's the reason why we do not want organic ACI, but we want inorganic ACI. If I go to cell results, you can see between S1 and S2, remember S1 is no BDC, S2 is BDC, and you can see the first formation cycle at 0.1 C. You can see how the voltage versus capacity, specific capacity plot, how while charging and discharging there is a big difference. So how the performance is down in the case of black color S1, no BDC, and red color is being upheld where we have BDC. You can go from 0.1 C at first formation to third formation to fifth formation to 100th formation at 0.2 C, and you can see that in the case of S2, red color, the charging and discharging, they are all maintained, but in the case of black, the charge in the case of discharging, this has been has been a decrease in the black color, which shows that there is a decrease. And when we do the impedance spectroscopy in the case of black color, which is no BDC, there is an increasing polarization resistance. Red color, there is a BDC, and there is a small impedance spectroscopy or electrochemical spectroscope. The polarization resistance is high in the case of black compared to the red. Okay, so S1, S2, S1, no BDC is black, so polarization resistance is high. Red is there is a BDC and polarization resistance is low. So that means it is protecting it, the material. So I will take another 2 minutes or 3 minutes, Professor Faisal. So I just at the end talk about a little bit on this structure that one of our PhD students worked on, neodymium-cobaltite, which is being doped with strontium and iron, which in MIC, very good MIC electrode material. So we can use solid oxide fuel cell as solid oxide cell. Solid oxide fuel cell, you use hydrogen as a fuel. You use nickel wise as the anode, or your NSCF, the one that I told you at the cathode, and you have oxide ion electrolyte, which is oxide ion conducting electrolyte, which could be YSZ or GDC. And you can use a similar cell, NSCF and NSCF symmetric cell with the electrolyte for electrolysis purpose, solid oxide cell. So CO2 is electrolysis to CO, and oxygen, oxide ion gives an oxygen out in this case. And we are showing you through molecular simulation that when you have this doping, there is a increase in the pathway of the oxide conductivity. So we can show that oxygen vacancy formation energy in the case of the NSCF is low, minus 38 kilocalorie per mole, which is negative, and that means easy oxygen transform or transport take place through NSCF. And we have found out also this calculation through the ab initio or the DFT calculation, and the spontaneous formation, vacancy formation at 38 kilocalorie per mole, which is kind of spontaneous oxygen migration by a jump of an oxygen ion from one octahedron to another octahedron in the linear, that means one from here to here can easily take place. And that is how, by doping, we felt that we will improve the oxygen conductivity and as a result cell performance. Here again, we are showing you the same NSCF structure, and then you have the doping. And so we have NDO polyhedra and cobalt oxygen polyhedra formation. And here the EDAS, the lattice spacing, everything tells about that we could make the NSCF iron strontium doped neodymium-cobaltite. And then now we are showing NSCF conductivity. You can see very high electronic conductivity. Arrhenius plot, electrical conductivity relaxation we are trying to show. And here we're showing the density of state calculation. And from there, we can show you the valence band and conduction band. And these bands are close to Fermi level. They are overlapping. And that is the reason you have got very good electronic conductivity in NSCF material. That is the reason why you have such a nice overlap of CBM and VBM, the valence band and the conduction band that we have shown. And now we also did an oxide ion conductivity by a blocking cell method, that we allow only oxide conductivity and no other conductivity take place when we put a material, the MIEC material enclosed by only the oxide ion conductor, no other conductor. So when we did that, we did a ab initio calculation on DFT to find out the oxygen migration energy calculated through using nudge elastic band NEB method, and we got this relaxation relative energy is about 0.45 electron volt. When we calculate that Arrhenius plot and activation energy, we got about 0.48 electron volt. So this is about 0.45 electron volt, that activation energy, and this calculated from the Arrhenius plot about 0.48 electron volt, which is almost like matching that the way we thought that we will get very good oxide ion conductivity when we doped with cobalt and when we doped with strontium in neodymium-cobaltite. Okay, now we made the cell. We make nickel YSG as anode functional layer, YSG and GDC. This is a electrolyte, so we have the GDC electrolyte, YSG to enhance the oxide ion conductivity at the interface. So we have the functional layer. Then we have NSCF GDC, this kind of a mixed material of GDC and NSCF, so that you have both the conductivity MIEC takes place and you have NSCF here. And we could show that solid oxide fuel cell mode, the power density goes to about 2.3 milliwatt per centimeter square, which is quite large, at about 3.2 ampere per centimeter square. At the black color is about 800 degrees Celsius. Even if I lower to 750 and 700 degrees Celsius, I do get about 1 ampere or 1.1 ampere ampere per centimeter square of current, which is quite good. And even at 750 degrees Celsius, we get about 2.25 or 2.25 milliamp ampere per centimeter square, which is a good current that you get about 0.8 volt or so. A good power density. That's a solid oxide fuel cell. Then we use solid oxide cell and CO2 electrolysis to convert to CO. We got an extremely good current, as we are showing you here. In the case of NSCF, GDC, NSCF symmetric cell, when you have GDC, NSCF as a kind of a functional layer, so that we have a graded conductivity difference between the different layers. So that is how we got this blue color and little larger power density, which is about 0.2 watt per centimeter square. A reasonably good current density, as we are showing you here, and voltage less. When we have this less polarization resistance with the functional layer, the red one, compared to the no functional layer like GDC NSCA functional layer, we added very good current density maintained up to about 55 hours. And this is symmetric CO2 symmetric SOFC, and this is symmetric CO2 SOEC. And where we got an when we see the SOEC performance, we got a current as close as about 1 ampere per centimeter square. And it shows that when you have functional layer with NSCF, we have a less resistance, less polarization resistance. So every way it is making sense. And time is up. I had a topic on ion implantation. So we use a mass spectroscope to do a selective ion implantation, and I'm not going to go details. We can see our work. This is a collaborative work with Purdue, that at ease we can specifically implant iron, which is polyoxometallate. So we take polyoxometallate, let's say molybdenum 12 and oxygen 40, a very complex structure. And we can just, because of this mass spectroscope with a magnet, we can, and voltage, we can specifically implant only the cation, not the anions. Okay, anions are oxygen, cations are molybdenum or sodium. We can preferentially do that. That is been done by Purdue, but we have utilized this material, and this is how it is showing that preferentially we can take, utilizing this material, we have able to implant. We have a cations and anions in polyoxometallate, like you have a tungsten oxide, but we can only put a complex structure like this in the form of tungsten, and the cations and anions, whatever we prefer, based on the charge and the magnet that we use to guide them through that. And we can also count the number of ions that we want to implant. So we had a strategy to do that in our lab, which we are showing you here. This is an ion implantation chamber. And as I said you, because we call it this as a lens, so when we spray that in a electrospray ionization chamber, and we have these ions, cations and anions, then both are going through this a little heated and activated through a charge difference, and then only one of them is passing through this zone, not the we did it for the cations, and anions are left behind, and then we deposited it as we are showing you here. And because of that, we got a very good supercapacitor performance as shown you here. So we could get about 8 ampere per gram of supercapacitor performance by POM, polyoxometalate tungsten oxide, as we are showing you. And the performance of supercapacitors at 10 millivolt per second scan rate is shown you here. This is the potential versus specific capacity, 8 ampere per gram. And the table shows the performance. When we put an ion coverage, we can count the number of ions that we can put. You can see that number of ions 2.5 into 10 to minus 13, and we increase it. The POM loading, nanogram, the polyoxometalate, how many of them deposited, and the mole number. We have a specific capacity of 388 farad per gram and about 53 watt-hour per kg. And that's what we have achieved, a supercapacitors, which has been published, as I said, in small. This is that we published my student Arya Das, along with Julia Laskin, who is our collaborator from Purdue. And we learned from Julia about this technique, but they were using to detect the cancer cells. They work in different areas. We were using this to make ion implantation in the case of energy storage system. So we did that, and I end here. I'm sorry that I've taken 7 minutes or 6 minutes more. And this is a summary. I talked about 3D printed electrolysis cell, membraneless. We talked about ZIF8 used as a anode protector or a ACI for zinc ion battery or zinc aqueous battery. Boron doped carbon is protected for NVPF, so that you have a inorganic ACI, not organic ACI, which deteriorates the cell performance, as you shown you here. Lastly, NSCF in detail, which is the iron strontium doped cobaltite, neodymium-cobaltite, used as an electrode material for both SOFC and SOEC. SOFC for hydrogen oxygen as a fuel for producing electricity, and CO2 for reduction. And we got a very good current. And lastly, we have talked about that polyoxometalate, a very controlled deposition or ion implantation for supercapacitor application. I must acknowledge the funding that I get from different funding agencies, including government bodies and different industries, Mitsui Kinzuku, IREL, ACE Green, Verdine Chemicals, and many our governments, and then all my PhD students who have been tirelessly working in our lab and the postdocs. Thank you. Thank you for your time, and I'm happy to ask any question. I'm extremely sorry that I've overshoot the time, but I have a lot of topics to cover. We started a little late. Thank you.
No worries, Professor Basu. Thank you very much for your very insightful talk. It looks like you're working on very exciting subject from fuel cell to electrolysis and capacitor and battery. That is really very timely. So we can take some question in brief. So there is a question from Venkateshan from Teesside University is asking, he need to know phosphonates as a host for iron cobalt transition metal ion. Did you try nickel based system?
That was phosphonate, so that was having nickel. So it was, I talked about that cobalt iron phosphonate, which I presented, and I did work on cobalt nickel phosphonates and nickel iron phosphonates. So of course I am presenting very good results. The rest of the results I'm not presenting, because you have seen that I am presenting so many results or so many ideas and so many things that we have achieved in last about 7-8 years. And I did work on nickel system as well, but the best results we got with the iron cobalt phosphonates. Nickel we do not standard alkaline electrolysis is a nickel phosphonate or nickel phosphide in NIP is a lot of people have reported. We also developed it, but this gave the best results when we are talking about specific results regarding the structure of the phosphonate that we wanted to have. But nickel phosphide does give a very good results, as we also know. I have seen people worked on it and presented, means documented. We also found out a similar way. It does work well.
Thank you. There's another question from Venkadeshan. Did you measure electrochemical surface area?
Oh, yes, definitely. We have done everything, but you cannot present every work. We did find out the ECSA. We did find out the BT surface area, which is like physically how much surface area you are creating, electrochemical surface area as well. And it does make sense in terms of the result that we have got. We do get a very high ECSA.
Thank you. I've got a couple of questions, very briefly, if I may ask. I really like your presentation on cooking, baking, and tarka, which help us to understand in a simple way how we fabricate those samples. So I work in high temperature steam electrolysis, and in recent weeks or couple of months, we have engaged with various stakeholders in the UK, trying to understand the challenges in integrating high temperature electrolyzers. So from your experience, could you suggest is there any opportunity in times ahead to develop technology in high temperature or mid-range temperature range electrolysis?
Are you asking this question? High temperature means what the temperature range? Are you asking in terms of the solid oxide cells in that context, or high temperature even at other kind of electrolyzers?
So what I understand, there could be, say, distribute the temperature up to, say, 800. So anything from 600 onward may be high temperature. How about mid-range from 400?
Yeah, so we all right now in our lab, we are all trying to work in the mid-range, intermediate, and even at low temperature as well. So we mostly working on proton conductors for that, and we did good success on proton conductors, but not so lower temperature, about 650. We do get a very good results for proton conducting solid oxide cells. But it's not that durability is an issue. Always we have BZCYY if you are working with the proton conductors. We do have a problem with the longevity of the cells and durability of the cells. We also are looking at an alternate proton conductor. So yes, it is quite possible. I think everybody is looking at, even people are working towards the 400 to about 600 degrees Celsius solid oxide cells with the proton conductors. And that's the looking forward outlook I would have in future, that slowly bring down the temperature. I only could do up to 650. We wanted to do about up to 500, 600. We will be working. I think that is the way forward. And I see that some people do report at that temperature, but I have not seen myself. We couldn't do that ourselves, but I mean, I'm sure it is possible for the proton conductors, not for the oxide conductors. I mean, difficult probably. Oxide conductors 650, 700 is what is at the most you can do it possible.
Indeed. Thank you. One question from me is, we are doing techno-economic analysis for steam electrolysis. And we all know the current market rate is around £10 British pound per kg. And if we are looking for future opportunities in this energy vector, do you think we can bring it down to 1.5 pound per kg or around that number?
I thought that 10 pound per kg is a little higher number. I would say it should have been between 5 to 7 or 6 to 7 pound per kg. I thought. I thought it is between 2 and 3 is possible. Are you talking about including the cost for compressing it or storing it?
Well, it means we have to do full techno-economic analysis so that it becomes sustainable in the sector.
Yes, so I find that we did an analysis. So in the case of, you're talking about hydrogen, right?
Yes.
Yes. So we did big analysis when we are trying to have a hydrogen hub and hydrogen valley in India. So there are hydrogen valleys and hubs are coming up. And the cost when you are talking about pressurizing to about 50 bar, 100 bar, 200 bar, the cost is because of the compression. The kind of energy that you have to spend to compress it is what is killing us. So when you say 10 pound per kg, because you out of 10 pound, 7 pound is taken away, or 6.5 pound is taken away by the compressor, the cost. So if we not talk about mobility, if we just simply talk about industrial use, I do not require very high pressurizing the hydrogen except for the ammonia plant. If the Haber-Bosch process or the modified Haber-Bosch process, the pressure is much lower. It's not at 200 bar. The modified Haber-Bosch process is much at lower pressure. But of course, ammonia, if you want to make ammonia, then you're required to pressurize it, but that is an additional cost. But if you want to deliver hydrogen at lower cost, at lower pressure, then it is quite possible to bring down the cost to about 2 to 3 pound or $2 to $3 per kg.
Okay, we can take one more question, which is from Abdullah, and I can add my question as well. Means commercialization is a challenge in low carbon hydrogen these days. I can see in the UK it is not so easy. There are a lot of challenges. So what is your experience working in this domain for many years? Do you think it is a good opportunity in times ahead?
I am thinking that it is a good opportunity because there are tenders now, because many countries said that they want to be carbon neutral by 2050, 2070. If you need to do that, you cannot do it overnight. So you have to have some pilots running from today to see how you can have a green steel, how you can have green ammonia and things like that, or petroleum industry, how you can use hydrogen from renewable sources, not from the fossil fuel sources for hydro treatment and things like that. So I see that in the industrial use, this is a possibility that in my context, I see that maybe the alkaline electrolyzer, although in the Western countries, I'm talking the perspective from Asia, mainly from China and India and South Asia, that mostly the alkaline electrolyzer, the cost is low, but you have more maintenance. So if your labor cost is not very high, that makes sense to start with, and you could really get a hydrogen at lower cost compared to the PEM electrolyzer and SOEC electrolyzer. And then by that time, and that 20, 30 years, you might be able to build your technology in this, like in PEM and in SOEC, so that you get hydrogen much durability and lower cost, which is not today. But to have a business case, maybe today alkaline electrolyzer is the best bet.
Thank you. I think we are coming to the end of the session. I'm so sorry we ran over by 21 minutes. So I've got one request. We are doing a survey as part of METASIS research. If our audience can spend 10 minutes, that will be really useful to us. And also you can browse. We did a workshop in summer this year. And feel free to read the workshop outcome on high temperature electrolysis and the opportunities in that. So thank you very much, everybody, and especially to Professor Basu for your very insightful presentation. Once the video is available, I will share the link with you.
Thank you. Thank you very much.
Take care.